We're going to continue talking about signal processing and specifically thinking about LTI systems, both continuous and discrete versions of this. And one of the things that we want to talk about are some of the fundamental properties that are important in signal processing. And once you make the assumption of an LTI system, there's some very nice properties that hold that we're going to exploit as we start constructing solutions. So first of all, just as a reminder, this is your LTI summary, your linear time invariant system summary of solutions. Whether I'm in the discrete case or the continuous case, the discrete case, right, the way I get a solution is I take my input signal. The input signal induces a response, which is characterized by H, and if it's time invariant, it does not matter when I kick it, I get the same H. And so I integrate over this, where essentially every time I kick it, I get the same response, and I add these all together in a sum. And so one shorthand notation for this is this convolution operator, which is x of n, h of n, which represents this summation. You have a corresponding version of this in the continuum limit, y sub t, which is an integral of the signal convolved with the response h. H is, again, the fundamental response to a delta function kick, which then can be represented here. It's in a box. It's a box formula. So every engineer, every scientist knows that if you have a box formula, it's super important. This is one of the most important pieces of what we do for LTI systems. That's the summary of LTIs right there. And in any case, you start to understand right away, if I want to construct solutions to LTI systems, I have to know the response to a delta function kick. So that's going to be an important thing that we're going to do throughout this course, is understand if I kick the system with a delta function, what's the response? And once I have that, I have everything. I know everything about the system. I know how to construct all the solutions I need with that kick. Okay? So that's the basic that we want to understand. And then, of course, we want to understand some of the underlying mathematical properties that also hold for LTI systems. So let's start with a simple example, and then we're going to move into some of the properties. So for instance, suppose my response, h of n, is that if I kick the system at delta n, in other words, at n equals 0, get a kick. What this says is, at 0 everywhere except for where you kicked it, at n equals 0, and at n equal 1. So in other words, it turns the function on for 2 steps, and it goes back down to 0. So let's suppose that is the fundamental response to a kick. Then my solution is pretty simple to construct. Y of n now is going to be something like this. This thing only comes on at, for 2 time points at n equals 0 and n equal 1, so I can just add these together because all it's going to do is multiply my signal by this amount here. So this is a very simple representation of a solution for a very simple dynamics from the kick itself. Okay, so you can start constructing these. Very rarely will you be able to, do something as simple as this, but, it just represents essentially the architecture, which is sum up the solutions based upon what the fundamental behavior is from the kick. Okay, so let's start talking about properties. And these are generic properties that hold for these LTI systems, discrete or continuous. The first one is the commutative property, which is essentially, if I look at this function, x of n convolved with h of n, remember this is my fundamental solution form that I'm going to integrate, it is equivalent to switching these around, h of n, x of n. So all you have to do to get from one to the other is do a change of variable. So you can easily represent your solution in this way, just like we did previously, which is with x of n and h of n here. Okay. Similarly, for continuous functions, x of t, h of t, this is the convolved solution that you would get. You can flip the order around so that you, in fact, have h of tau, x of t minus tau. So this is another representation of it that's absolutely equivalent. And in fact, let's just derive this here. Here's the derivation of this. So first of all, h of t convolved with x of t is given by here. And what we're going to do is just do a change of variables. change of variables, we're going to call xi t minus tau. In other words, that's the argument here. I'm going to call that xi, t minus tau. Then dxi is minus d tau. Remember, integrating over tau. So here it is. So if you just plug that in, what you end up with is now the limits change. This goes from infinity to minus infinity in this new variable, right? Because you've got the minus sign right there. And you also have a minus sign in the front of the d tau, which is here. So you get h of t minus c, x of c dc. And if I flip this, that takes care of that minus sign. And so what you end up with x of c, h of t minus c dc, which is h of t convolved with h of t. So notice what I've done here. I've just flipped these simple change of variables. Okay, so it's important that you recognize that you have this commutative property and it holds for all of these LTI systems. You also have distribution or distributive property that's there, which is if I convolve x with, h1 plus h2, it's the same as x convolved with h1 plus x convolved with h2. I mean, these are all properties that flow directly from linearity. Remember, your basic operation is on an integral in this convolution, and integrals have this distributive properties, and so this is not surprising. It holds. It's pretty simple. This is also what it looks like here in terms of the continuous case and the discrete case. So both of these hold these properties across there. So another way to represent this graphically is through these block diagrams. So you take your input signal, and it says, well, okay, I'm going to operate on x1 and x2, and then combine them. That is the same as h1 and h2 being combined, and then the output there. So these are equivalent representations based upon this distributive property. So, or another way to say it, if I want to graphically represent this distribution property, here it is. Okay, these are equivalent representations. So that's a nice way to represent it as well as in that graphics. I can add this commutative and distributive property together, so I can have a sum of two signals convolved with h of n. It's the same as signal times convolved with h, signal times convolved with h as well, and just add those together. Okay, so that is the overall commutative and distributive property put together into one representation, both for the discrete case as well as for the continuous case. So these properties are super important because we're going to leverage them all the time in creating our solutions, and we're going to use them when they're convenient for us to more easily construct solutions as we go forward. You also have associative properties. The associative properties around kind of what we normally think of as multiplication. And so here what you have is the convolution of x convolved with, in parentheses, h1 convolved with h2. So notice these are both responses, h1 and h2, to signals, right? So they're convolutions. And what it says is it doesn't really matter the orders of the operations here. If they're linear, then you can easily first take h1 convolved with x of n, and then convolve with h2 versus doing h2 and h1 first, then and xn. Doesn't matter. Same thing in the continuous case. So this associative properties is nice. Again, what you want to do is, if it turns out to be easier to calculate this way than this way, you would just do it because you have this associative property holding. Again, another graphical representation of this. You can think about x coming in, being convolved with h1, which produces some signal, let's say call it omega, which then gets convolved with h2, which finally leads to your output. And what this simply says is, well, x1, I could just write this as h1 convolved with h2. So instead of producing an immediate signal and then process the signal again, I can just convolve them into one function. And it doesn't matter what the operation is. In other words, I could do h1 first or h2 second or vice versa. And so I could just reverse those and do h2, h1, and then break it back out into this here, which is x of n. First gets processed with h2, then h1, then the y output. These are all equivalent. So what it's telling you, at least, is these convolutions, it doesn't matter the order of operation, right? That's this associative property. These operations, I can do them however is most convenient for myself, whatever's the best way to represent it in practice. So those are sort of some of these important properties that hold for these linear systems. We also want to talk about other properties that are more associated with the response of the system. The first one we're going to talk about is a memory in the system, or no memory in the system. So for instance here, if I want a memoryless system, in other words, think about what H is. H is the fundamental response to a kick. So if I kick the system and it produces some response over time, then as I kick it the next time point, it now relies, my solution now relies on the fact that, well, it's still settling down from the previous kick. I add that together, but now I have a memory effect. So if I want a memoryless system, in other words, I kick it and I should have no memory response, it means that H of n, right, which is the response to the system, is 0 everywhere except at the kick. Okay? So there's very few systems that are actually completely memoryless. Most systems, when you kick them, there's a finite time response till it settles down. But if there's an instantaneous response and it's back to 0, that's a memoryless system. Okay? So this is what it means to be memoryless. I kick it, it has an immediate response, but no other n produces a response. In other words, there's no response downstream that persists. So what does this give us? Well, in some sense, h of n is just some constant times a delta function then. This is the way to think about it. If only one value matters, which is the current time, it's that current time times some constant k. So I could just write it something like this, where k is some h naught, or h0. That is the fundamental response, is just whatever the kick is, has an immediate impact and then goes away. So the memoryless solution is actually trivial to compute. Because I kick it, the response comes immediately, and then when I go to the future and kick it again, there's nothing to add. Whatever happened from where I kicked before is already gone. So when I kick it, I just get the response immediately from that. So I have h of n is only acting on k delta n. And remember, I'm going to convolve my solution against this h of n, but the h of n is a delta function, which acts as a sifting function, which means my solution y of n is just k times x of n. In other words, I just sift out the value of the signal exactly at that point, which is by strength k, and I get the value that I need. So that's a memoryless system. If you have that property, this holds right here. Okay? In some sense, it's the easiest system to consider, right? There's no time history. You don't even have to do integrals anymore, because those integrals have a delta function in them which sifts the single value out. Okay? So that's in the discrete case, and if in the continuous case, it's the same thing here. Then we can talk about invertibility. So do we have invertibility or not? So what are the kind of properties that we have here? And invertibility is really around this concept of, if I have a response, h of n, can I invert that response, let's call it h1 of n, so that when I convolve my response and its inverse, I get back to the delta function. In some sense, this is exactly the definition of invertibility. I do something to the signal. Can I undo the signal uniquely to get back to a delta? And so this inverse problem is very important. So how do I find this operation? This is in discrete and continuous. So in other words, if you have a signal where you say, oh, my operation is when I kick the system, I multiply by 2, then the inverse is divide by 2. That's a very simple system, and it's super easy to find the inversion, right, which is multiply by 2, multiply by half. They're inverses of each other. It's much more complicated when you have a time dynamic response to trying to find the inverse of that time dynamic response. Okay? But in certain cases, it can be done. And you asked the question about invertibility. We always hope that we have, if we're going to try to find something that's invertible, that we can write down a simple representation of that invertibility. Okay, so here it is in sort of block diagram form. I'm coming in with a signal x of t, right into here, this first block h of t, right? So this is my action of my signal, which produces an output. I run this output through h1t, right? So here's my output of that signal, and what I want to produce then is back to my original signal over here. Okay, so the process is you come in, you do something, you undo it. That's what inverses do. Whatever you did, you just undo it. So really, at the end of the day, if x of t is going to be max to x of t, then it better produce a delta function, right? It just should say, well, if this is going to go to this, it's like multiplying by 1. Okay? And this is, of course, a convolution, so you really want this thing to be a delta function, and that gives you back this idea that I can map my solution back to itself. But notice how you're doing it. You're first undergoing an operation and an inverse of that operation. So that's the idea of an invertible system, is if you can actually do these things here, right? Is you can actually find this h of 1 to do this, or find a unique h of 1, right, that could do this. Okay, let's talk about causality. Causality is really important, actually. And it's generically, I think everybody has a pretty good intuition of what causality means. If I kick a system at some time, let's say at time 0, then the system reacts to that kick. So in the future, I could have a reaction. So I kick it at time 0, and at time 1 and time 2, time 3, there's some response that maybe it dies down. But I can't kick it at time 0, and in the past, something happens. Right? I kick it at time 0, and at x and time minus 10, all of a sudden something happens. That breaks causality. It breaks the arrow of time. So the way I think about this is h of n, which is your response, is 0 for all n less than 0. In other words, it cannot go backwards in time and turn something on. It's important that, when we think about systems in our world, in our real world, they better have this causality relationship correctly done. Okay? So this is typically something that you'd have, and the only time causality doesn't hold is something like, I always think about the Marvel universe where, Doctor Strange and Tony Stark have special devices that break all of causality, right? And we can go backwards in time. But, we're building real systems here. Causality is an important property to hold. Okay? So causality has some implications. In other words, causality allows us actually, if we use the fact that we have, this property, we can write our solutions by essentially, we don't care if the convolution of the solution is x of t star h of t or h of t star x of t, but if we reverse that, then we know that here, h of k is 0. This is always 0 before k equals 0, and then it can be positive. In other words, this sum now doesn't go from negative infinity to infinity, it goes from 0 to infinity because h of k is 0 everywhere for k negative. This is a causality issue. It means when I kick the system, it can only react in the future. Same thing here in continuous time. This h of tau is, I don't have to integrate this thing for tau is negative infinity because this thing is 0 there. So I can just start the integral from 0 to infinity. From the current time forward, what is the reaction to the system, right? There's a future time response it has to the system, and you can't kick the system and create something that happened in the past. Okay? So causality relationships are going to be important to preserve, and here are these causal relationships explicitly assuming that h is 0 for time going backwards. Okay, last concept, which is around stability. And we're going to talk a lot more about stability as we go. But stability is really, again, all of us have a pretty good concept of stability, which may be a way to say it here. If I give you a bounded input, it produces a bounded output. So that's at least the stability in the sense of this signal processing. And there's a lot more to be said about stability, and we're not going to say too much more about it here. But certainly it's of intense study in dynamical systems, this concept of stability. But here, just sort of this is your layman's version of this, or your in words. If I'm going to put in a signal, I don't want this system to blow up. That's it. So I want the system to be stable, right? And not run away and produce infinite or massive solutions or huge solutions, runaway solutions. So another way is to do this is when I think about my response, the absolute value of my response, it is the absolute value, here is the response now written in its convolutional form, which is h of tau, x of t minus tau. I integrate this, And now you can use some of your integral relationships, these bounds on integrals, which is the absolute value is this, is less than or equal to the absolute value of each of those functions over that domain, which is less than or equal to, if I'm assuming that the signal is bounded. In other words, if I assume the signal is bounded by B, then it's basically limited by this response. In other words, what it's telling you is this integral better be finite. And what it's then telling you is that H itself, when I kick the system, it doesn't produce infinity. Okay? When I kick the system, I get a bounded reaction to my delta function kick. That's what this is actually telling you. Okay? If this, however, goes to infinity, that's a problem. So that would be a disaster. And this is like the unstable system. I give it a kick and it goes to infinity. That's not most systems, right? That's kind of the way you think about systems. I kick the system. What's the response? A lot of times the system responds and then dies back down to the solution you want. There are cases in which you kick the system, you break it, or maybe you start to go to a very different solution type, which then would create this thing to be essentially going towards infinity, and then that system would be unstable. Okay, so those are some concepts we want to work with. So first of all, all of them become important. We're going to use all of them to our advantage in what we do. But some of them are important from a philosophical point of view, like causality. We expect causality to hold, right? We expect when I kick a system that there's a finite response in the future. I don't kick the system, there's a response in the past. I want the associative property. I want to be able to do the commutative property, because these are going to all be important when we do signal processing for LTI. They have these very beautiful properties we can put together and start to engineer systems based upon the fact that we know that these properties hold as we move forward. Okay, that's it for some of the properties of LTI systems, and we will continue to work on this and develop solutions for the LTI as we move forward in the next lectures.